right, so today I'm gonna presenting the study carried out by my PhD student Chris Sala in collaboration with Dr. Enrico Zorato at uh, New Mexico New Mexico Tech. And this is my first time participating in this discussion series. So thank you for inviting me, and I'm very honored to be presenting here and hearing your feedback to our study. Um, okay, so the biggest motivation for this study is because the US summer precipitation, it shows two hot spots. So if we apply the EOF analysis to the summer precipitation over the United States, the dominant mode we got is a dipole pattern between the US Midwest and the southeastern US. So if there's decreased precipitation in the US Midwest, we tend to see increased precipitation over the southeastern US. And this dipole pattern accounts for 38% of the interannual variation of summer precipitation over the United States. So it indicates the southeastern US summer precipitation is one of the hotspots that really needs our attention if we would like to better understand and predict the year-to-year variation of rainfall over the entire country. And another motivation for us to focus on the southeastern US is because if we are pulling out the precipitation record for the entire domain and we perform a domain average, what we get from the past 70 years of record is that we see the variation or year-to-year deviation of the precipitation from the mean becomes its amplitude become larger. So that leads to increased occurrence of both the dry and wet summers. So for example, in the earlier period of the records, there were 2 wet years and 2 dry years. But if we are looking at the records that is post 1978, 5 dry years occur together with 6 wet years occur, indicating those abnormally either wet or dry events tends to become at least doubled in the more recent decades. And people start to look at what causes this rainfall variability increase. And one explanation is the North Atlantic subtropical high has extended more westward. So the North Atlantic subtropical high is a large-scale high-pressure system that is situated over the 30-degree north of the North Atlantic Ocean. And during summer months, the high can intensify and it brings the moisture along its western edge into the southeastern US. So if we overlay the precipitation distribution over the North American and also North Atlantic together with the geopotential height isoline that represents the subtropical high, we can see the increased precipitation, or we call it rain belt, generally aligns well with the western edge of the North Atlantic subtropical high. So what happened to the high in the past decades is that it tends to extend more westward into the southeastern coast of the US. So if we are lining up the location of the western edge of the subtropical high and color code the location according to decades, we can see in the earlier part of the records, those blue dots are located relatively eastward compared to more recent decades. Those red dots tend to located more westwards compared to the climatological location. So the hypothesis is that once the subtropical high is located more westward, then it's more easily transport the moisture from the ocean into the southeastern part of the United States. So with the increased oceanic influence over this region, then the year-to-year variation of the subtropical high western edge location tends to have a stronger influence of precipitation over here. So this hypothesis is based on the fact that the oceanic moisture transport play a very significant role in modulating the precipitation of the southeastern US. But however, it remains unclear where the moisture sources is located for the southeastern United States summer precipitation and what modulates or what's the role the subtropical high plays in modulating the moisture transport pathway that makes the oceanic water landing over the southeastern US. So that comes to our research question, and our aim of this study is to use the WEM2 to track and thus address the moisture pathway and transport mechanism for the southeastern US summer rain. So our first question is, what source regions are supplying moisture to the southeastern US summer precipitation? And to further address this question, we decompose the total precipitation into three different categories because as what we learned from meteorology, the rainfall system that generating different amount of precipitation are quite different. So for example, the heavy rainfall events over the low latitude, like where the southeastern US is located, tends to be associated with more deep convection system, like the passage and landfalling of the hurricanes tends to bring in large amount of precipitation into the region and create heavy rainfall events. But for light rainfall events, they are usually more associated with the large-scale frontal systems. So those rain generating system, their mechanism behind are very different. And from there, we would expect the moisture source region and moisture pathway supplying those rainfall events is going to be different. So our second question becomes how the moisture source regions differ across different rainfall intensity category. And we also would like to address how the moisture is conveyed from the source region to the southeastern US differently across the different rainfall categories. So our first analysis is to look at the rainfall categorization. And in this analysis, we apply a statistical inference using a Bayesian Gaussian mixture model that we, according to the AMS definition of the rainfall, we separate the rain events into the light, moderate, and heavy rainfall category. And then we are using the localized data to determine which category of the rainfall, which category a daily rainfall event has to be located. So I'm leaving the equations of the Bayesian stats model over here. And I would like to draw your attention to the contribution of the each rainfall category or rainfall cluster to the cumulative precipitation of the southeastern US. So the color-coded are different categories of rainfall. The red color-coded is light rainfall. Black color-coded is moderate rainfall events. And blue color represents heavy rainfall events. So what we can see here is that if for a given summer, the light rainfall events account for majority of the rainfall, then overall, we tend to get decreased summer rainfall events, summer rainfall total over the southeastern United States. But if more rainfall falls into the heavy rainfall category, we can see there's a linear increase of the total precipitation as a function of the cluster contribution of the heavy rainfall, indicating if more events falls as a heavy rainfall, then the entire summer tends to receive increased amount of total precipitation. So we recognize heavy rainfall events as an individual meteorological feature. They are happening at daily time scale. But from this analysis, it showcases if we aggregate those daily contribution, the heavy rainfall cluster makes a large contribution to the summertime overall hydrometeorology over the southeastern US. So figuring out the moisture source and moisture pathway difference between the light and heavy rainfall is thus not only of meteorological significance, but also of the climate and hydroclimate significance for the region. So to track the moisture source and moisture pathway for the southeastern US, we are using the WEM2 model, and we are backtrack for daily precipitation over the southeastern US, which is marked in this red box. And we are performing the backtrack for 15 days and then perform an average over the 15-day backtracking period. So according to this figure, those color shaded are the region that are making significant moisture contribution to the southeastern US. So the total, if we are summing up over the entire region that is color coded, it accounts for 95% of the total moisture that are responsible for the southeastern US summer precipitation. So according to this analysis, the color shading are mostly over two regions, the eastern US, the terrestrial region, supplying moisture to the southeastern US, and there are also a broader region covering the Inter-American Sea and part of the subtropical North Atlantic. They are supplying moisture into the southeastern US from the oceanic sources. So this is a climatology, but the moisture contribution from those source regions differ quite significantly according to the rainfall categories. So the figure on the left shows the moisture contribution amount in the unit of millimeter per day. And we can see if we are increase the intensity of the rainfall, almost every moisture source region tends to contribute more moisture. So for example, the light rainfall not only sees decreased moisture over the local area, but the moisture contribution also decreased over the oceanic region. But the heavy rainfall, not only the local contribution increases, but the oceanic contribution, as well as the extent of the oceanic source region, tends to expand, providing more moisture to sustain the heavy rainfall events over the southeastern US. To emphasize the importance of the land versus oceanic moisture sources, we also computed the percentage contribution anomaly for the different rainfall categories. So now, from here, we can see for the light rainfall contribution, it shows a more important land contribution at the red color, indicating increased percentage of moisture contribution from the local are mainly located over the terrestrial region. But for the oceanic region, we can see a significant decrease of the moisture supply as indicated by this bluish color. The heavy rainfall events, its moisture contribution or moisture importance is very different from the light rainfall. It's almost in contrast pattern. So overall, the contribution or importance of the land area significantly decreases, but the oceanic contribution significantly increases, especially along the Inter-American Sea, which generally co-located with the southern edge or southwestern edge of the North Atlantic subtropical high. And it indicates the Gulf of Mexico's Caribbean Sea is making more moisture contribution than normal days for the heavy rainfall events. And this increased oceanic moisture contribution is indeed has something to do with the North Atlantic subtropical high. So this is a figure showing the moisture contribution difference between the heavy rainfall events and light rainfall events average. So again, reddish color means more contribution from a given location. The blue color means less moisture contribution. And we are also tracing back from day zero, that is the day when the event's onset, back to 12 days ahead to see the evolution of the circulation and evolution of the moisture source region. As we can see from the day zero, there are increased oceanic moisture contribution to the southeastern US for the heavy rainfall events in comparison with light rainfall events. And if we are plotting out the geopotential height isoline representing the North Atlantic subtropical high, we can see the red color representing the light rainfall events and blue color representing the heavy rainfall events. We can see, the reverse is true. The red color represents heavy rainfall events and the blue color represents light rainfall events. We can see during the event day, the North Atlantic subtropical high is much intensified during the heavy events. At the same time, the western edge of the subtropical high is located relatively eastward compared to the light rainfall events when the subtropical high western edge extends all the way into the southeastern United States, creating a high pressure over the land area, which preventing the oceanic moisture to be transported into the southeastern US, so depress the precipitation. And the intensification of the subtropical high starts to come out almost a week ahead. Further than that, there are no significant difference in the subtropical high circulation systems. Overall, a week before the event's onset, we can see the most significant change in the subtropical high is over the central region, when we see a center intensification of the high, which leads to intensified easterly wind along its southern portion. So it promotes increased evaporation of the ocean, which tends to provide extra moisture supply, which can later on transport it along its western edge into the southeastern United States. So at day 4, as the subtropical high further intensifies, more moisture along its southern and western edge is induced by increased evaporation associated with intensified wind. And those evaporative water from the ocean surface is directed towards the southeastern US. And at day 0, those moisture start to arrive at the southeastern United States to supply the heavy rainfall events. So overall, from our study, we conclude that the heavy rainfall events explain 78% of the total interannual variation of the summer rainfall over the southeastern US. And those heavy rainfall events, its occurrence and the moisture sustaining mechanism are very different from the light rainfall. So overall, during the heavy rainfall events, there are increased oceanic contribution moisture from the Inter-American Sea into the southeastern United States. But in the light rainfall events, they tend to derive more moisture from the local and land sources. For the heavy rainfall, the increased oceanic moisture are transported into the southeastern US along the extended western edge of the North Atlantic subtropical high. And as a discussion, that is a work in progress. What we are looking at is what causes the North Atlantic subtropical high to start to intensify a week ahead of the heavy rainfall events. And what we look at and what we found is that the wave stream pattern over the North Pacific Ocean tends to be quite different in the heavy rainfall events in comparison to the light rainfall events. So overall, for the heavy rainfall events, there seems to have a wave train that is sourced over the eastern Japanese Sea and then transported all the way downstream uh, into the eastern US. And as the day goes, the high and low as a part of the wave train tends to intensify over the North American continent. And it indicates probably there's some wave train interaction that originally originating from the Pacific Ocean start to interact with the rainfall and moisture transport over the North Atlantic sector. We are still working on the detailed mechanism. So hopefully from more wave analysis, we can figure out what causes the subtropical high to intensify and provide a more effective moisture regulation mechanism for the heavy rainfall events. Okay, so I will stop here. Thank you for your attention, and I'm happy to take your questions.